Hello guys, welcome back to my channel Gamma Di Gamma. So in the last video I believe we classified singularities in different types and sort of determined a way to find the order in case there were poles. So in this video I'm going to talk a little about residue calculus, what residues of singularities are and why are they important. So let's get started with today's work. Why do we actually care about residues? Well, here's a quick example for that. Assuming you have I, which is the contour integral about some contour C, dz w of z, where w is some, again, complex valued function. Well, let's kind of draw C. So C is something like this. It can be any shape. Just being a little arbitrary here. Well, I'm assuming that we can expand the function w of z in terms of a Laurent series. And we can do this under the assumption that the region enclosed by the contour C is, or more likely, or a better way of putting it is, contour C is within the region of convergence. So assume you have some pole here centrally Z0, and then you have some maybe singularity out there, and then between them you have sort of the region of convergence. If you remember, a mixed Laurent series had that as the region of convergence, like the region in between, the disk in between two singularities. So it's not really like passing through this Z0 circle, but it's sort of in that region. So we can expand W of Z as a Laurent series about Z0. Well, okay, again, you can see that Z0 is sort of deemed to be a pole. I'm doing this for poles first, simple poles rather, or one pole. More than even simple, let's say one pole. So I'm expanding W of Z using a Laurent series about Z0, and since it is within the sort of the annulus of convergence, we can write this as a Laurent series because it's guaranteed to converge or give us both positive and negative terms. So let me write that we have both positive and negative terms. We guaranteed that. Okay, let's move on. So if I can expand W of Z using a Laurent series, what I can do is just make a substitution. Instead of W of Z, have the general form of a Laurent series. So n goes from negative infinity to infinity. C sub n, z minus z0, because we're expanding about z0 raised to the nth power. And again, since we're assuming convergence, we can interchange the sum and the integral. Otherwise, this requires a fairly rigorous sort of convergence criterion. For now, we're fine. Again, we are in the region of convergence, so that should be sort of a relatively logical explanation for this. I can do some cases now for n greater than or equal to 0. That's case 1. Well, notice what happens. We just have some positive terms. Alright, we'll have something like integral over C dz C sub n z minus z0 to the nth power, and we're basically summing from n equals 0 to infinity. Well, the way this series is written, z minus z0, because, well, that term If it's in the denominator, it will cause us problems, right? Because we know that we have a pole at Z0. So if this term's in the denominator, it will cause us problems. But if it's in the numerator every time, Cn is just a constant coefficient, then it doesn't matter whatever we have, our integral will always be 0 because of Cauchy-Grusha, because there are no poles, there is no singularity, as long as z minus z0 is in the numerator, which will hold true for this case where n is greater than or equal to 0. Okay, what about case number 2? Well, the case when n is less than or equal to -2. Well, if you sort of write this out, dz, and we have c sub negative n plus 1, I believe, divided by z minus z0 to the n plus 1. And then you sum from 1 to infinity, if I'm not wrong. Yes. Well, you notice this form is sort of like the nth derivative. So we'll basically have 2 pi I divided by n factorial, nth derivative of basically the Cauchy's integral formula, which will be nth derivative of this coefficient evaluated at z is equal to z0. So the coefficient is a constant. It's going to be some complex number. So well, the nth derivative of a constant will always be 0, irrespective of what point you're evaluating it at. Okay, this is for, say, this was for n greater than or equal to 0. This was for n less than or equal to -2. Well, we have the last case. The only sort of number that remains is n equal to -1. Why that case is particularly special is because wait, I actually, you know what, there was actually no need for this sum. I was just wondering about this. We don't really need this sum. I just tried to show that each individual term of this was like 0. So we can drop the sum if you want, and same thing here. Because if we take the sum here, I have to take another sum here. All I want to show is that each individual term of this, you know, when you sum them up of the series, they become 0. As long as n is less than or equal to 2, or the other case is n is greater than or equal to 0. So only for these two cases, each individual term will become 0. So if you add those terms, you'll obviously get 0, as long as these two conditions are true. Apologies for the slight confusion there. For n is equal to -1, actually, we have this term dz c sub -1 over z minus z0. And this, you notice z0 is like the only singularity in there, only pole over there. We can use our Cauchy integral formula to get 2 pi I times the function evaluated at z0. The function is like c sub -1, which is a constant irrespective of where it's evaluated. So the answer for this contour integral is 2 pi I times c sub -1. So c sub -1, this coefficient, is what we call the residue of the singularity z equals z0. So in other words, what we had was, we had contour integral over c dz. We had the sum from -infinity to infinity of c sub m z minus z0 raised to the nth power, which was precisely, before making the substitution, integral of w of z. This, if you see, well, for all the positive semi-definite terms it's 0. For the negative terms that are less than or equal to -2, they're all 0, and the only term remaining that's non-zero is this. So in this entire sum we just have one non-negative non-zero term left. So 2 pi I times c sub -1, which is precisely a result that is kind of intuitive, or you might have seen this before. I actually started with kind of this result in the complex analysis playlist before even covering this topic. So it's 2 pi I times residue at sort of the only pole that's enclosed in the contour, which is z0. This was the case for when we had one single pole inside the contour of integration C. What if we have more poles? Do we sort of change this formula? How do we generalize this? Because it's kind of hard to see right now. So let's move on to the next page for that discussion. Okay, so moving on to our next discussion, assume our function w of z is something that has the form f of z divided by z minus a, z minus b, and z minus c. So we can safely assume we have 3 simple poles. Because again, simple because I'm not raising it to any power, so it's going to be order 1, all 3 of them. And f of z we assume is analytic in the appropriate region. And again, the region will be sort of around the contour like before. So if we have like a contour C here, well, our region okay, so I'm just gonna like sketch these guys. So assume like A is here, B is there, and then like C is outside somewhere. Then like the region of convergence is going to be something like this. So from like this C boundary to boundary of A, and then from C boundary to boundary of B. So the thing is, we're going to have to split our integral, and this splitting is kind of makes sense because we are deforming the contour. So we are going to deform contour C and going to write it as a sum along contour C1, which is this guy, and contour C2. And again, the appropriate region is sort of this region, this annular region between C1 and the boundary of C. Oh, sorry, this dotted boundary, and also like the boundary, the region between C2 and the boundary, the dotted boundary. So that's like the appropriate region where we expect f of z to be analytic, because we really don't care. Actually, for this, f of z has to be analytic just inside C. We don't care if it's non-analytic outside, because we always consider the behavior of functions inside the contour, because if it's non-analytic, then we have to take another pole, which may not even be a pole. That singularity may not even be a pole. So let me just, f of z is analytic within C. We don't care if it's like non-analytic outside, but we want the entire thing to converge in the annulus. So the Laurent series, whatever we're going to find, converges in annulus. I think this is a better description of our conditions or our assumptions that we have. Okay, so I said contour deformation. So let's say I is contour integral over C dz w of z. I can write this as contour integral around C1 dz w of z plus contour integral around C2 dz w of z. Again, this is contour integration. I haven't shown the small intricate details, but you can sort of use the same approach that we use for Laurent and Taylor series part 2. Okay, so if you find basically contour integral around C1, you're gonna have to expand the Laurent series about z equals a for the first guy, and for the second guy you can expand, or you should expand, the Laurent series about z equals b, because those are like the only poles that are enclosed. Because after we deform the contour, then our focus sort of diverts into smaller pieces. So for integral over C1, our focus is on this contour of integration C1. So we only care about things that are inside. So the only pole that's inside is z equals a. So what we're doing is we're splitting up a problem with multiple poles by contour deformation into problems with single poles. And this is basically just like the previous page, because this now becomes 2 pi I times the residue of z equals a for the first C1 plus 2 pi I times residue of z equals b. And since like we are taking different Laurent series expansions around different points, so it makes sense that like the residue is also going to be different. So to kind of generalize this idea of multiple poles, we can come up with this nice formula. We have 2 pi I times the sum of residues of poles enclosed within the contour of integration, which is C. I mean, ultimately, although we sort of found C1 and C2 separately, all of these are ultimately within C, because C is like the biggest contour that encloses these guys. So I hope that makes sense. I hope this is a good way to generalize. I hope this is not too hand wavy for you. And again, this is again assuming the Laurent series converges at within, or rather within that annulus. And we again only care about things that are inside C, not stuff that's outside, like this point C. This point C is just like sort of a way to limit the region of convergence. If this C wasn't there, our region of convergence would go until infinity, and we would just have some real terms, some positive power terms. So it would be a Taylor series, I think, not a Laurent series. But the principle, the mechanism works the same way. This is the grand formula we need to work with, and we have been working with this. If you see like the initial videos in my playlist on complex analysis, I didn't derive this, I'm deriving it now. So I hope it makes sense now. Back then I just, found the poles, the residues by a method, which I will be discussing shortly. So let's move on. Okay, so let's talk about first order poles. Well, now that we know that the residue is basically the C minus 1 coefficient, so if we have some first order poles, our Laurent series expansion would look something like this: C sub minus 1 over Z minus A. Since it's a first order pole, the most negative this power can get is just a minus 1. So we just have this term, and then everything else is a positive power. This is a most general representation of a Laurent series of a function with a first order pole. Okay, and this goes to infinity. Well, for this, to find C sub minus 1, what we can do cleverly is multiply both sides by Z minus A. So we just get C sub minus 1 plus C naught times Z minus A, C1 times Z minus A squared plus C2 times Z minus A cubed. And then what do we have? Well, what we can do now is take the limit as Z goes to A. As soon as we do that, notice these on the right hand side, this goes to 0, this goes to 0, and this goes to 0. Only thing that is remaining is C sub minus 1. So we have limit as Z goes to A W of z times z minus a. The limit of this guy is nothing but c minus 1, which is the residue that we actually needed to find. This was for first order poles. What about higher order poles? We can generalize this method. Okay, to generalize this approach, let's see, again, order n, right? That's why order has to be finite, otherwise it's not even a pole then. So if W of z is equal to, then it's going to look something like c sub minus n divided by z minus a to the n. The most negative you can get for a higher order or order n pole in general is n, and then c sub minus 1 divided by z minus a, and then c naught c1 z minus a, and then till infinity. Well, for this, what we can actually do is again trying to repeat the same. So multiply by z minus a raised to the nth power. So c sub minus 1 minus n plus c minus 1 z minus a to the n minus 1 c naught times z minus a to the n c1 times z minus a to the n plus 1, and so forth. Well, the issue is, if we now take the limit as e goes to a, everything else will go away. Even c minus 1 will go away, and we'll end up with c sub negative n, which we don't want clearly, because the residue is c sub minus 1. So what we can do is we sort of want to like reduce the powers, like get rid of these n minus 1 powers on c sub minus 1, so that we end up with like no z minus a term multiplied with c minus 1, a condition that was similar to this, and then we can take the limit. So the best way of power reduction, at least for this, is a derivative or taking derivatives. So let's just take the first derivative with respect to z. You have W of z minus a to the n, and we have, well, this first guy goes away, it's just a constant. So if the n minus 1 c sub, well, I believe c sub minus 1 z minus a n minus 2. I'm just skipping like these intermediate terms. I'll just put like yeah, plus n times c naught z minus a to the n minus 1 plus n plus 1 c sub 1 z minus a to the n, and then until infinity. Well, so there's like this pattern going on, but we still want to reduce this n minus 2 to be power 0, so that this z minus a disappears. Notice the pattern. You take the first derivative, the power of this guy associated with like this n is, well, n minus 2, right? Take the n minus first derivative, you get a negative n plus n, which is 0. You take the nth derivative, you're going to get negative n plus 1 plus, I believe, let's see, n, so you get negative 1. So let's take the derivative n minus 1 times, because we want 0 power for that. So doing that, we have n minus first derivative with respect to z of W of z minus a to the nth power, and then again, once you do this, you end up with, for the first guy, we have n minus 1, n minus 2, n minus 3 for all the derivatives. So we have n minus 1 factorial c sub minus 1 plus n factorial c naught z minus a and like all the other terms. So we still have the z minus a. Now what we can do is now we can take the limit as z goes to a, because that ensures that like this guy becomes 0 and all the other terms become 0 because they have increasing powers of z minus a. So we're just left with c minus 1 times this factor, which means c minus 1 is nothing but 1 over n minus 1 factorial limit as z goes to a, n minus first derivative with respect to z of w of z minus a to the nth power, like that. This is the formula for the residue of pole of order, and you can substitute like say n equals 1 and you get like this for the first simple pole case. And yep, I think that this is a good formula, and this formula is what I used extensively at the start of this playlist. But now you know where it comes from, and now you know sort of the logic behind it and how it's connected to this entire concept of residues or Laurent series. Okay, so we had this formula for the residue of a nth order pole. Well, these were for the discussions were for poles. What about essential singularities? Well, the issue is that we can't use this formula because for essential singularities, if you remember my last video, and again I urge you to watch that because this won't make sense without it. For essential singularities, we had this order term, this n for like the most negative your power can get in the Laurent series expansion. This goes to infinity, so there's no limit to how negative it can get. You have all the negative powers from the Laurent series. So like whatever you do, you may or may not have all the positive terms, but you sure as hell have all the positive terms. So if I write this as well, the Cn in this case will never be 0. The Cn in this case may or may not be 0 depending on your region of expansion or point of expansion. So you kind of see we can't use this because the infinity factorial, you'll have to use a regularization. It's not standard. Then infinite derivatives, infinite powers, it's not the right way. I mean there might be some sort of like regularized version for this, but there's no like easy way for this. There's no easy way out for this. Well, if you recall what the residue was c minus 1 coefficient of the Laurent series expansion around that singularity point, where for a essential singularity, a function with an essential singularity inside the contour of integration, you of course need the residue to solve that. How do you do that? You expand Laurent series. That's what I'm saying. There's no easy way out. Using like this factorial calculation, you could have skipped that for poles, because again poles can be skipped. They're removable singularities. Expand the Laurent series and then directly find c sub minus 1 in the series. So assuming you have something like this integral e raised to 1 over z dz, contour of integration is this sort of circle that is enclosing the origin, which was the singularity point, the essential singularity point. So the answer of this guy is going to be 2 pi I, because we discussed this, times the residue of z equals 0, which is an essential singularity. So if we expand e raised to 1 over z, as a Laurent series about the singularities equals 0, we're basically going to have terms like 1 plus 1 over z plus 1 over 2 factorial times 1 over z squared plus 1 over n factorial times 1 over z to the n, as n goes to infinity, because it's a infinite, series are infinite. So if you so what you do is, for finding the residue, you just look at the power of z and just pluck out the coefficient where z is -1. So well, z is -1, it has to be power 1 in the denominator, which is basically this term. So you pluck out the coefficient. The coefficient of this guy is 1. So you have the residue of z equals 0 of this function is 1. That's the coefficient. So this integral by our well-derived formula is going to be 2 pi I times 1, which is 2 pi I. Believe it or not, something that actually blowing up at 0, take a contour around 0 and you integrate, find the contour integral of that, it doesn't diverge. It's actually a finite answer. So you notice how nice this is. This is a really powerful tool that we will be using in probably the next few videos that are left. So what did we do until now? Well, we discussed complex functions and variables, which was sort of, trivial, assuming you know what complex numbers are. Complex numbers. Then we discussed about their differentiability rules. And so that gave us like the Cauchy-Riemann conditions. If you remember, we discussed their integration. So that gave us, we use like Stokes' theorem in the proof of that, the Green's theorem in the proof of that, gave us Cauchy-Gursa and Cauchy integral formula, and also like the nth derivative version of it. Then I took like a break, which I shouldn't have taken, but I had to obey an order. Then we came to Taylor and Laurent series. So you understood how to expand a function, when to expand it, what's the region of convergence, and how it depends on what sort of what your contour encloses, whether your contour in between two poles, two singularities or something like that, or not. So how that depends and how that changes and how that converges, we talked about that. And then after we have that in our bag, we talked about what types of singularities are, because we wanted to sort of extend out into the today's topic of residues. And we discussed what was the motivation for finding residues, is because if you expand a function using its Taylor and Laurent series at that singularity point, so this is how these things are connected. The only term that survives from the Laurent series expansion is the residue term. So the integral is basically going to be, as we discussed, 2 pi I times the sum of residues inside the contour. So I hope you kind of see like the motivation or like a chain of motivations that were going on, especially in the last three things. Once we discuss series and discuss singularities, we could apply both of them by expanding this function in the integral as a Laurent series about the singularity. We reasoned that the only term that remains from the Laurent series expansion is the c-1 coefficient times 2 pi I, which we called the residue at that singularity point. So I hope this kind of clears things up, gives you a little more perspective. We're going to use this nice theorem to do many more examples of calculating some real integrals using complex analysis. So we did some like questions based on that without proving it or without any like firm basis, but now we're going to do it way more formally. So stay tuned for that. That's way more exciting. Please like, share, and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. In the meantime, stay home, stay safe, keep doing math, and peace out. Stay tuned for more content.